Perfect. Okay, great. And let's just, perfect. So thank you all for coming out today. I'm Jeffrey DeRose, the director at the CSI Technology Incubator. And the purpose of our institution is to help drive economic growth through, through entrepreneurial education, technology education, and also through events like this, right, where we're bringing in speakers of color to come and educate you guys about different career paths. I just want to give a quick thank you to Verizon for sponsoring this program. Verizon wanted us to develop a workshop series that would help build more diverse pipelines into technology. And so we developed this speaker series that some of you have been a part of. Today we have Kayla Lee with IBM from Quantum Computing. And Kayla, I could just give you the floor to introduce yourself, and you could jump into your presentation whenever you're ready.
Awesome, thank you. Let me see if I can get my screen sharing. Awesome. So thank you again for having me. I'm really excited to talk to you all just about my journey to quantum computing. So in this talk, I'll say a bit about myself and my background. I'll tell you a little bit about some of the things that I learned along the way. And then we'll dive into the interesting stuff. So what quantum computing is and why I think it's a really reasonable career for people to start thinking about. My goal for today is that everyone leaves at least knowing what quantum computing is and how it might impact their lives. And ideally for some people to even try programming a quantum computer. So would be really excited to hear anyone tell me about how this has been and if they actually managed to program a quantum computer. So I'm Kayla. I am a scientist by training. I have a PhD in systems biology. I did that after undergrad. And so I started undergrad just being really excited about science and biology and solving biological problems. I wanted to be a professor, but once I got to graduate school, kind of changed my mind a little bit. And at that point, I entered my career at IBM. So I'll tell you a little bit more about that journey. But in general, I'm a plant mom. So I'm traveling for work now, but normally you can see a bunch of plants in my background. I'm an older sister. So as I mentioned earlier, I have a younger brother and younger sister who are not that young anymore. But both of them are engineers by training that went to Clemson University. And then I'm just a lover of all things related to education and sustainability. And so this is career number one, but I definitely imagine in future careers doing things that really dive into more education and just sustainability and thinking about ways to make sure that the world that we live in remains good for future generations. My fun fact of the day and something that I want you all to ask yourself is, what did you want to be when you grew up? And so, we start as little kids saying what we wanted to be. Some people want to be an astronaut, ballerina. I think nowadays people want to be like YouTubers and influencers. But I was a super weird kid. So when I wanted to grow up, it was my dream to be an IBM executive. A lot of that is because of my dad. So insert picture of me preparing for my future as an executive. And what's really crazy about thinking about how this has always been one of my goals is honestly how close I am to being here. And so just by background, I have moved around a lot. So all of these little circles are places where I've lived because my dad was an IBMer, which some people know as I've been moved. I was born in Florida, spent some time in Arizona, went to Virginia, did my high school experience in Philadelphia. So I'm a Philadelphia sports fan all the way. Went back to Virginia for college, hung out a little bit in Alabama, went to grad school in Boston. I currently live in New Jersey, but spent my first 3 years after grad school in New York. And I'm actually planning to move to Charlotte this summer. So I've seen a lot of different states. I spent my undergrad at Hampton University, where I got a bachelor's of science in biology. I then went on to do my PhD in systems biology at Harvard. And since I graduated, I've been at IBM thinking and working in quantum computing. I have 3 quick things that I just wanted to share with you all as kind of like facts and tidbits that I learned along the way. So one of my claims to fame at Hampton University was while I was a biologist, I was one of the only people that did not want to go to medical school. Blood terrifies me. It still terrifies me. And so I knew that while I was really interested in biological problems, I was less interested in working directly with people. And so that's really what started my journey into science and what I thought would be biotechnology. And so I use this as encouragement to not be afraid to be the only person in the room that's willing to try something new. And so I was actually in my freshman year, it was toward the end of the summer. I didn't know how I was going to spend that summer. And our professor asked, who in the room doesn't want to go to medical school? I was the only one that raised my hand. And after that, she introduced me to this professor that really started my career in research. And so that professor took me under his wing. I got the opportunity to do research at so many cool places, including Yale University and the Broad Institute of MIT and Harvard. And that's what really validated that I wanted to be a scientist. And so I know it sometimes feels weird, especially in like tech and some of these more STEM related fields. You might not be the only one really interested. You might be the only one really interested. And so I encourage you to take advantage of that and use that as a strength. My second skill or tidbit I'll say is to invest time in gaining a new skill. So my PhD is in systems biology. For those who aren't familiar, this is a field that really takes biological problems and asks how can we solve them with tools from physics, computer science, and mathematics. So I worked in a lab full of people that come from a lot of different backgrounds. And one of the big things that I learned in grad school was how to program. And I think that because I had more of a technical biological degree, that's really why I was able to convince people at IBM that working here made sense, because most people at IBM actually don't come from a biology background. And so really invest the time in gaining or learning a new skill. And I said bonus points if it makes you happy or is relevant to current trends. And so things like deep technology, like programming, like quantum computing, they're all the next big thing. And so being able to think about what the next big thing is and what role you could play really plays a big role in the long term. And you have such an advantage by getting into a field early, although you'll feel like the only one. So just thinking about that as you're starting to figure out what things you like to do and what you want to do more of. And then finally, leverage your network to learn what else is out there. So the job that I have today, I don't think I knew that this job was possible. And I'll talk a little bit more about careers and what it looks like to work at IBM. But the truth is there are so many different jobs out there, and they're not the titles that we grew up hearing. So it's much further beyond doctor, lawyer, and engineer. And so just getting a chance to know different people, what they're doing, what they like about their job and what they don't like, are all things that are so useful in your career journey. And it's a reminder that your career is absolutely a journey. And so just because you start somewhere doesn't mean that you have to stay there forever. At IBM, I've had a few different roles. So I started as an intern in healthcare life sciences. That's really what made my bridge from my PhD to IBM. So I did our computational analyses. I loved research, but did not want to make that out of a career. And so instead, I was really interested in the intersection of business science and technology. So I started as an IBM Quantum Computing industry consultant. That's where I learned so much just about business and enterprise clients. So what does it mean to work with companies like Nike, like Pepsi, like FedEx, and think about how quantum computing could impact their business? After that, I was a product manager. And so I was really interested in just learning more about what product management meant in the tech field. And so for people that are less interested maybe in traditional software engineering, product is often a really great place to end up. So I spent a little bit of time as a product manager, and then my manager actually left, and so it was an opportunity to do something new. And so I led our academic partnerships, and now I'm the global lead of our partner experience and operations. And so I lead a small team that's really focused on building up the IBM Quantum Network. And my fun thing is that in 2021, I was named in MIT's Tech Review's 35 Innovators Under 35. So to switch gears, I want to tell you all about quantum computing. And I like starting with this picture. So on the left, you have a picture of the first electronic digital programmable computing device. You can see it's pretty big. You don't see screens like you're used to, and it's mostly wires. And then my other fun fact is that back in the day, the original computers were women, so they actually call women computers. For those that have seen Hidden Figures, I'm sure you've heard of that. And then once people realized that computing was actually a profitable career, that's when it switched more to a male-dominated field. So women don't give up. And then today you have next to it IBM Quantum, which was the first universal quantum computing device that was made available to the public. So I'll tell you a little bit more about all that you're looking at. But I think the important thing to take away from here is that we're really at the beginning of what quantum computing could be. And so just like back in the 40s, where we didn't quite know where programmable computers would take us, that's also where we are with quantum computing. And so while we know there are a few really exciting things that we might be able to do, it's also research we're all still learning. And it's really one of my goals to ensure that we can create pathways so that more people can get engaged. The idea of a quantum computer came from a well-known physicist, Richard Feynman. He has this quote that I think is great. So I'm not happy with all the analyses that go with just classical theory because nature isn't classical. And if you want to make a simulation of nature, you better make it quantum mechanical. What's really important to take from here is that nature, so everything around us is quantum mechanical, and the way the subatomic particles work is super counterintuitive. And so it's not the way we understand the world. And so if we ever want to be able to simulate nature, we need to think about nature in the same way that it does. And so that was the hope and the promise of what quantum computing could be. And so if you take a step back and look at our history of quantum science, just to tell you where we've been, but where we're going, it really started in 1935 when Einstein and a few of his friends got together and just noticed how funky some things in quantum mechanics are. I'm not sure if we have any people that are physics majors or have taken a quantum mechanics class, but hopefully you'd be able to just relate to the fact that there are some things in quantum mechanics that just aren't that aren't intuitive. In 1970, it was really the birth of quantum information theory. So just this concept of how might we leverage quantum mechanics and information. In 1981, MIT and IBM hosted a physics of computation conference. And so that's really where scientists started getting in the room together to start thinking about what quantum computation could look like. And then if you fast forward to 2007, we have the transmon superconducting qubit. And so I'll say a bit more about what a qubit is later, but it's essentially the quantum version of a bit. And since then, we've launched quantum computers on the cloud that anyone can play with. And so it's been a long journey. And things here highlighted in blue are things that we've done at IBM. So we've been involved in this for the past 4 decades. It's a long journey, but where we are now and where we're going is what's exciting. So we started with this field of quantum science, which is really just building the physical blocks of quantum computing. We're now in this quantum ready era. So we're starting to engage and excite the world about quantum computing. And we're at the brink of quantum advantage, which is essentially when we get to a point where we can do something on our quantum computers that we can't do on today's classical computers. And that's the exciting part, when we can actually start solving problems that we can't solve on today's classical computers. So what is quantum computing? To summarize it with 3 main takeaways, so these are the 3 things that if you all leave here with, hopefully it's these. It's a new model of computation that leverages principles of quantum mechanics. We're experimenting and doing research to better understand potential applications. And so when people say quantum computers can do this, the truth is we're still figuring out what sorts of problems they'll be great at solving. And then it has the potential to solve problems that are intractable on today's classical hardware. And so do not think about quantum computers as just being a faster classical computer. Instead, we're thinking about really big, massive problems that our classical computers just can't solve. So this is what a quantum computer looks like. I want to walk you all through kind of what you're looking at. And if you recall that first picture I showed in the cylinder, this is what goes inside. And I have another picture to show you. So we call this a chandelier. What it actually is something called a dilution refrigerator. And so with each layer that you go down in the chandelier, the system gets colder and colder. And so at the bottom here, you see this little black chip. That's the quantum processor. It operates at 15 millikelvin. And so just to put that into perspective, the temperature of outer space is 2.7 Kelvin. At 0 Kelvin, that's absolute zero and nothing moves. And so just above 0 Kelvin, we have this quantum chip, and at that temperature, it's able to do some really, really funky things. So that's what allows our qubits to actually behave quantum mechanically. And so this is a quantum computer. What you imagine the actual system looking like is this. So you send some signal from a classical device. These are your qubits. It goes then to some sort of electronic system, so kind of like those cables that we saw. It sends microwave pulses down to that dilution refrigerator. Those pulses then go to the qubits. It causes them to do something, and so the pulses cause them to rotate, or you manipulate them. Resonators read those signals. It's then sent back to your classical computer, and it's read out as a binary number, something like a 1 or a 0. I went fast there, but we can chat a little bit more about what that is when we have time for questions. But essentially, you have this full system. So you still have classical computers. They're doing some sort of electronic control and then some sort of wave manipulation. It goes down to your quantum computer. It's then sent back to your classical computer. Oops. And so if you were to take a step even further back, you have at the bottom your hardware and systems. On top of that, you have circuits, templates, and pulse schedules. And so these are something we call libraries. Above that, you have algorithms and applications. And so let's say you don't really care about the details of the hardware. You just want to know how you can use this to solve problems. And then above that, you have tools and services. And so this layering here is what we call a stack, the quantum computing stack. It looks pretty similar to what you would have as a classical computing stack, except for it's much smaller in our current world. And so one of the things that I'd love for people to take from this slide is that at each layer in the stack, there are people that are solving really hard problems. So let's say that you're currently an engineer, you're really, really excited about building things, getting your hands dirty, like you'd be great for a hardware engineer. And my absolute favorite thing about quantum computing, but also working at IBM, is because software and platforms have become so big, I feel like the art of hardware is kind of dying. And so that means that people that really do like building things and getting their hands dirty, sometimes in the tech world, it doesn't feel like there's a place for you. But at IBM, we're really, really focused on building the best quantum computers there are. And so we have people that are focused on fabrication of devices and those sorts of things. So great skill for people that like to build things. Your libraries, those are like your lower level developers. So once again, the people that back in the 80s were kind of building on motherboards and computer chips, they would fall there. Your algorithms and applications, so those look much more like your classical developers and data scientists that are building things. And then people like me actually fall on the top. And so I'm more on your services side. So how do we make all of this relevant to others? So let's do a little bit of fundamentals, and then we'll switch gears and talk a bit about careers. Quantum computation uses qubits, and so I've said that word a few times throughout the presentation. In your classical computer, you have either ones or zeros, and they could only be a 1 or a 0. Those are bits, they're binary. A qubit, on the other hand, we have it represented here as a gradient and circle, but really you could think about it as a sphere. And so on your sphere, you have poles, either a 1 at the top, a 0 at the bottom. And then you could imagine this line between your poles. That line could then rotate based on those microwave pulses that I mentioned earlier. And so now, instead of just being a 1 or a 0, it could be some linear combination of anywhere in that state. And so these numbers are complex, but they actually look a lot like nature properties. And because of this feature of being able to be in what we call a superposition of states, we're able to see a large number of states, much larger than you might see on a bit. And so while a qubit is being manipulated, it's in this mixture of states. Once you measure it, it then collapses on either 0 or 1, which is why in that animation, you saw 2 ones at the end. And so essentially, there are 3 main principles that we like for people to think about when they're thinking about quantum computing. So the first is superposition, that idea of being in a linear combination of 1 or 0. The second is entanglement. And so this is what actually allows qubits to talk, interact with each other. And so something that's interesting about quantum computers is if you had 2 perfect qubits, they're able to scale so that your power is 2 to the n. And because of this, this is the big opportunity in just scaling that we have with quantum computers that doesn't exist with classical computers. And then the third factor is something called interference. And so interference, think about waves where they can either be constructive and add or destructive and subtract. In quantum algorithms, which are special algorithms that we use on quantum computers, this property of interference is actually what allows you to get to solutions faster. So pretty interesting. And 3 words that I want for you all to take away from today's talk. And so that is all fine and dandy. How can we actually use them? Quantum computers are not expected to completely replace classical computers. I've said that a few times. Instead, we think that there are a few different types of problems that quantum computers will be really great at solving. What you'll notice about these problems is they all scale exponentially. And so essentially that means as soon as you add one input, the solution search space grows. And so an example that we often like to use is if you had 10 people at a dinner table, how many different ways could you arrange those 10 people? And the fact is that number is actually pretty big. So it's 10 factorial. And so that's something that we call a problem that expands exponentially. And so things like simulating quantum systems, which explain exponentially because of how the atoms interact, optimization problems. So one of the classic ones that people talk about are something like traveling salesman, or just how you get from how you choose the best route. Machine learning, we just know that because of the large amount of data, understanding something simple like classification could become a challenging problem as it scales, and then risk analysis. And so think about this as the thing that financial institutions care a lot about. But these are all potential applications of quantum computing. And I have a few examples of work that we've done with companies in the past few years that I just wanted to quickly highlight. So one of our clients was Daimler Mercedes-Benz. So hopefully you all are familiar with that car. One of the big questions that Daimler came to us with, they're a great, interesting company because they are focused on building the next generation of car. And so one question is, what's the next generation of a car look like? We know that it's leaning and trending towards something that's electric. The challenge is that today's electric vehicles The battery size is limited. You can only go so far. And the actual material that you use to make those batteries is also resource limited. So there's a finite amount of cobalt in the world. And because of that, we need to research new ways to build electric vehicles, but specifically the batteries that power them. And so we did work with Daimler to do two things. The first was to experiment with new materials like lithium sulfur as an alternative battery material. And then the second was to ask the question, how can we make today's batteries last longer? And so what you see here is the quantum circuit that we use to measure the energy of one of the crystals required in lithium sulfur. Another company that we've worked with is JP Chase. And so hopefully you all are familiar with them as a financial services or bank company. One of their big questions is how to just better assess risk. And so most financial models are all underscored with this estimate of risk, where their big question is how do we minimize risk so that we can maximize our investment? And so we did something here that's called a quantum version of Monte Carlo, where essentially the idea was that we use the quantum computer where we were able to estimate the same amount of risk, but with 1/10 of the number of samples. So that's another way that we've thought about how quantum computing could impact financial services. And then finally, we're doing work with ExxonMobil. So you all should be familiar with them as a gas company. But one of the things that they're thinking about are what does the world look like without gas? And so they're very interested also in just what it means to build and understand advanced energy solutions. And so while some companies are like, these are big problems that we want to solve, Exxon actually asked the question, how could we use quantum computers to be more accurate in solving really small problems? And so a fun fact is that anything we do to understand chemistry or molecules is all estimation. Like we are not able to accurately compute even the hydrogen bond molecules, and that is because the calculation is just too complex. So everything we do is an estimation. And so because of that, if we're able to be more accurate with our numbers, we could actually start solving ideally new problems. And so that was one of the things we did with ExxonMobil. So I'll switch gears again and take a quick sip of water. Now that we have quantum computers and hardware that people can actually use, what comes next? So teams at IBM are focused on the future of quantum computing from a few dimensions. The first is research and development. And so research and development are traditionally people that have PhDs or at least advanced master's degrees. They're really focused on building quantum computers or building the software that goes on top of that. They are theorists, researchers, engineers. They write papers like a person that has a PhD might do. And their main goal is to just add new research and knowledge to the field that contributes to IBM's main goal, which is to build a really big quantum computer. There's a team of people that are focused on business and industry applications. And so this is where I fall because I work primarily with partners that are interested in building on top of IBM Quantum. Most of the people that I work with also have PhDs, but instead of just doing research, we're really interested in the intersection of research and technology. And in our case, having more of a technical background helps just communicate between both C-suite executives, but then also researchers and scientists. And then there are people that are on the community and adoption side. And so one of the things that's also really important to us is building a community of developers. And so oftentimes these people come from more of your classical developer or even education background, and they're all focused on how do we get quantum computing in the hands of more people. And so when you're starting to think about what careers could look like, using this framing and just asking yourself what you're interested in doing can help. The core job functions, though, are really these three categories. And so there's researchers, there's developers, and there's engineers. I have a list that I'm going to show, but I don't want to stress people out. So I want to just walk people through the layers here. Your researcher, like I said, traditional likely comes from a PhD background, probably wants to keep doing research. And so those could be the experimentalists who are getting their hands dirty, your theorists, so more from a math or physics theory background, and then your application people. Your developers are pretty interesting because they're the people that are thinking about those different layers of the stack. So while it be the libraries and the microwave pulses, building new quantum algorithms or applying those modelers. And then you have your engineers. So your hardware engineers are building systems. Your software engineers are building the tools we need. You can be a software engineer in quantum computing that isn't doing quantum programming. And so one of the things that I'll tell you about is our quantum computing platform. All of that is classical. And so you don't just have to do quantum computing coding. Anyone with a traditional developer background is still like building our APIs and those sorts of things. We have internships. And so I just wanted to show people kind of a breakdown of where people come. We are still pretty heavy on the research and PhD side. So about 42% of our interns have PhDs, 32 come from an undergraduate, and 26% had a master's degree. And then of that divide, 15% are in the engineering domain, 35 in the researcher side, and then a core group of people that we have are different types of developers. And then this is something that I put here in case people wanted to screenshot it. And so this talks about the different roles, skills, and jobs that we hire into IBM. Historically, most people come from a physics, math, chemistry, computer science, or your double E's, your computer E's, or your mech E's. Obviously, that is not a rule. You can even be like me and a biologist and end up here. But traditionally, these are the people that we see that have the most success. And then what I did was highlight just the different functions in traditionally what their educational background is. And so you'll see it's the hardware and software developers that primarily have bachelor's and then master's. And then I included some of the key skills that we're often looking for. And so your people that are interested in research science are generally contributing to building the systems or building on the algorithm research. Your software developers are really the ones that are writing code and building software tools. So they have more of a traditional programming background. They know how to write programming languages. They know how to build graph algorithms. They're thinking about DevOps security, APIs, those sorts of things. We also have people that care about things like user experience design and user research. But that's much more of your traditional development background. And then we have these hardware developers, and so they're focused on advancing the development of quantum systems. So these are people that are interested in microfabrication, packaging, microelectronics, FPGAs, and different like radio transceivers. But think about all of the things that are actually related to building those systems. At IBM, a lot of the people that are in the hardware developer actually started as semiconductor designers back in the day from when IBM was still building PCs. All right, I have just a few more slides. So for anyone that was at all interested in quantum computing, what I would love for you to do is to go one of two places. The first is quantum-computing.ibm.com, and there you're able to program a real quantum computer. So we have several quantum computers that are available for free for anyone to use. They're smaller, but it's a great way to get started. We have lots of great documentation and also a really cool thing called a composer, where you're essentially able to drag and drop and build quantum circuits. So I'd say that's a really great tool for people that are just looking to build some intuition on why quantum computing is different than classical computing. If you're like, hey, this was great, I've actually already seen a quantum computer, I want to learn more, then I recommend that you go to qiskit.org/learn. And so that's where we have our full learning journey. If you are a PhD student that already knows what you're doing, we have labs you can start experimenting with. If you're super new, we have this cool just 3-hour course that essentially walks you through what quantum computing is, how it compares to classical computing, and even has some built-in coding exercises. So I think that it's a great place to start. And with that, I will leave you all with my LinkedIn. And if you're interested in quantum and a mix of some other things, you can also follow me on Twitter. And I will open the floor for questions.
Thank you, Kayla, for such an engaging presentation. I know I personally learned so much. And I think we had some questions in the chat, or at least some comments. But for the students in the room, feel free to ask a question out loud. You know, it's not every day you get somebody like Kayla giving you career advice.
Can I go?
Sure.
Yes, please.
Okay, thank you so much for this presentation. I had no clue that, you know, there were other people like myself out there. So you're giving me a lot of hope. Were you not having any doubt in your journey, like trying to figure out, you know, with that whole medical school thing, maybe people were trying to push you into that route. Were you not having any doubts in considering like what you wanted to do?
So no. And I think the reason for that is Black people are definitely more likely to go to medical school than they are to get a PhD. And so because of that, it was actually the opposite. Like professors were really excited that someone wanted to, to get a PhD. So I think I got a lot of attention because of that. And like, in fact, there are just over, my PhD is not in physics, but there are just over 100 Black women that have PhDs in physics. So like if you were to start your PhD tomorrow, you could be like 110. Like, and I know a lot of them. So it's crazy to feel like I know like 25% of the Black women that have had a PhD in physics. And there are just over 500 or 600 Black men. And so in general, I'd say that the PhD is just a little bit underexplored compared to your medical programs. And I'd say that, you know, everyone knows the career of a doctor, a lawyer, an engineer, but what you do with a PhD is a little bit less familiar. I wasn't that nervous because it was what I wanted to do. And I think that that's what motivated me, like just knowing that it's what I wanted to do. Like I said, I probably wouldn't make it a day in anybody's operating room. So that really wasn't even an option for me. But then I also had a lot of mentors that, like I said, encouraged me to go in that direction.
And my second question, I have my second question. So I when you try to explain like the actual connection between a biological process and how computers work and why, you know, we might need to have quantum computers to solve the really complex problems that the biological system and, you know, chemistry just poses to humans, you know, so that we can actually make like the new discoveries, especially like drug discoveries and all this kind of stuff. Like, do you find that people get it? Like, do you find that it's easier to explain this to kids or or to adults? Like, I know you say it, you're starting your like presentation, like you're starting to present to people, but like, who do you think is actually really starting to understand this message?
Yeah, that's an interesting question. I'd say that there's levels to understanding, right? So I can tell you a lot about what a quantum computer is, where it might apply, but I'm not going to walk you through all of the theory on how our qubits are built. And so with everything, there are levels to it. I think that people that are younger and still learning are just able to grasp the idea of this is something that works different. And then I've also found that the generations that actually played with computers before they were commonplace, so a little bit before me, they also understand it. So the people that are like, oh yeah, I remember vacuum tubes and those sorts of things, they kind of get it because they often think about quantum computers as analog computers. But the truth is, because there are so many different layers, like if you just go back to that picture of the stack, the expectation wouldn't be that you understand everything. Instead, it's what part of the stack do you find the most interesting, and then getting to know more of that.
Thank you so much for answering my question.
Yep. I see a question that asks, is this a silicon-based quantum computer? So the big part about a quantum computer is the chip. And so there are different ways that you could build a qubit. At IBM, we have superconducting transmon qubits. I do not know. And I do not think that they are silicon-based. But people are experimenting on what the best transmon conducting qubit is. And so I might be wrong. And there also might be people with silicon-based quantum computers, but there are lots of different ways to build a qubit. And so we have the transmon qubits. It has to be super cold. You have some people that have photonic qubits. And so those are based on light. You have people that have ion trap qubits. So those are based on like ions moving. You have people that have things called like NV centers and diamonds. So there are lots of different ways to build a qubit, and we have no idea which qubit will be the best. We're placing all of our money on superconducting qubits along with Google and some other startups, but there are lots of other ways you could build a qubit. I mean, so I'd say even that there's a little bit of a race to figure out which qubit is the right qubit. And then someone asked how I would rate the variety and adaptability of my work. My work has a lot of variety. So I spend some time doing presentations like this with students, with faculty and professors who also are very new to quantum computing, but then also with C-suite execs. I spend a lot of time building and creating content. That's things that our clients use. So you too can be a content creator in a corporate job. I spend some time just doing research and learning. And so I don't do it as much in this role, but I used to actually build small demos in some of my old roles. And then just time in front and with clients and making sure that they're successful. So definitely a lot of variety and adaptability. And I'd say that that's existed throughout my career at IBM. And so I've been here for just under 5 years, and I've had 4 different roles, all where I've gotten to learn a lot of different things.
Anyone else have questions? Feel free to unmute yourself and ask out loud.
So there's a question about being a software engineer, has never worked in quantum computing. If you apply for an engineer role, would you succeed? That answer varies a lot. If you are a skilled, traditional software engineer, and you are interested in continuing to do like traditional software engineering, so maybe you want to help build our quantum computing platform, you want to build the APIs that we're focused on for the cloud, and you're able to kind of pass your traditional coding exams, then I think you could be successful. For those that maybe aren't familiar, traditional coding exams, there are a few really great books, like Cracking the Coding Interview, I'd say is one of the more popular ones. But we're looking for people that understand general object level programming. So for people that are really, really new to it, I love the CS 150 class at Harvard. They are able to walk through code. So like even on the board doing pseudocode. For our entry level software engineers, they do have to pass the Hacker Earth exam. I don't think that's required for our more senior ones. And then general, they're just looking for your portfolio of work, whether that be at your corporate company or things that you're doing more freelance. Their day in the life looks much more like a traditional, I'd say, like product dev style of work. And so you would have a team, like you'd have a team of product managers, a team of developers or engineers. They generally follow on 2 to 3 sprint cycles. So for people that are familiar with Scrum or Agile, where the product managers help build a roadmap, and then the software engineers are responsible for delivering on those features. But I'd say that it looks pretty much like your traditional software engineer roles at any tech company. Any other questions or lingering thoughts?
I actually want to ask a question on behalf of the students. You mentioned the internship opportunities that you guys have. Just curious to know maybe what skill sets are needed. I know the computer science majors, like at least when they graduate for undergrad, they have to take like linear algebra, statistics, multivariable calculus, and they're spending 4 years working on C++. And by the time they graduate, they should have, some knowledge of algorithms and data structures.
Mm-hmm.
Here is, maybe what level of math, if they wanted to go for an internship, should they be at? And, does that profile of an undergraduate seem like someone who could be competitive in this space at an entry?
So there are a few ways I could answer the question. And I will say this in front of this audience, that having skills and having things on your resume in demonstrating the work that you can do are not the same things. And so that's why people love portfolios. It's why people will ask you for your GitHub link. It's why people like seeing your code, because they want to see the work that you have done. And sometimes learning something in class is not enough. And so taking a linear algebra class is great, but if you don't understand how linear algebra translates to complexity in the code that you're building, and if you build really bulky code because you don't actually understand some of the logic behind it, then you're actually doing yourself a disservice. And so I'd say that we value people that can get the job done over necessarily some of the courses that you've taken. And that's demonstrated by your portfolio, by looking at your work. And it is we can tell very quickly like what someone's programming skills are without asking that many questions. So I have worked with people that have graduated with computer engineering degrees that still struggle to write like a for loop or an if then statement. And that is not great. And just think about it, right? You're at a place where you're working with different engineers and developers. You're trying to build this production level code that thousands, if not millions of people are engaging with. And so the stakes are kind of high. And so we're looking for people that have competent coding skills. Like you should know what GitHub is. You should know how to interact with the terminal, which to me are very, very basic things. But like when people are doing the interviews, it's really to understand where your skills are. And so being able to, like I said, just walk through pseudocode. So for people that aren't familiar with the term, here's the fact. The language that you can write code in does not matter. How you think about code and how you approach code is what matters. And so pseudocode is really helpful because it allows us to see how you walk through your own logic. When I started my first day as my intern at my internship at IBM, I did a lot of my grad school programming in MATLAB. IBM does not pay for MATLAB licenses. So they were like, you're going to write code in R. And so you have to learn to write code in the language that the team is using or in the language that is best for whatever you're trying to build. And so we know that C++ can be really great at some things, but kind of clunky in others. And so it's understanding that and how you approach problems that we're really looking for. And then somebody asked a question just about remote roles or global roles. IBM is a global company. IBM stands for International Business Machines. Our quantum computing group, most of us are based in Yorktown Heights, New York. So it's about 45 minutes north of the city. That's where our research headquarters are. We also have researchers in Almaden, California, in Zurich, in Switzerland, and in Japan. That's where most of our research labs are, but generally IBM is a global company. So I'm one of the few people on my team that's here. We actually cover 6 continents of our team. So 30 people cover 6 continents. So we're pretty global, and there are often times where you get to travel and do fun things like that.
I think, Eni, you can unmute yourself, or I'll unmute you to ask your question.
Hi. Hi.
Hey, how you doing?
My name is Amy. I'm calling from Uyo, specifically in Nigeria. Some months ago, last year, I got mails for interns, and I gave it to undergrad here in Nigeria. Some of them did apply, but unfortunately, they were not shortlisted. And I want to know, what are the requirements? What do they need to do so that when the opportunity comes again, when they apply, they can be accepted?
That is a great question.
Yeah.
So I think that there are a few ways to answer that question. The first is actually the only thing that really matters is your resume. And so having a strong resume is really important. That resume, it should be clear like why we should hire you. And the thing that stands out the most is experience with quantum computing and Qiskit. And so we have something called a Qiskit developer certification. If you have that, that is something that stands out. There is a program called the Qiskit Advocates. If you have that, that is what stands out. And people that are Qiskit advocates also get paired with IBM mentors. And so then we know you, and we're actually generally looking for your application. And so I'd say that those are the 2 most obvious ways, the developer certification and the advocate program. But beyond that, the quantum community is actually pretty small. And so even doing things like chatting about your work on LinkedIn, getting engaged in the communities or the different meetups. We have a global summer school that we're not launching it. It's our 4th year in July. So doing that and having that certificate and badges, all of those are things that we notice. And then other than that, once again, having that strong GitHub portfolio, those are the things that make people stand out. I also truly believe in a good cold call. And so if you have people that you have kind of been following for a while on LinkedIn, like feel free to send them a note. I have a high schooler that messages me every year. She's been messaging me for like 4 years, just telling me about the different things that she's been doing in quantum computing. And I actually feel so bad because for the past 4 years, she's been like, do you have any internships for high schoolers yet? What about now? And so I can't wait till she graduates high school and I can at least have some internships for her. But yeah, so getting to know people, I have actually hired a few people onto my team that I've met from LinkedIn. So I'd say that those are a few ways to get started. And then actually, I think I noticed one of my work colleagues, Shay, on the phone. She manages a lot of our internship work too. And so she's another good person to just know.
All right, thank you.
Yeah, great question and answers, guys. Any other questions out there? Don't be shy. As you see, Kayla is full of knowledge. Yes, Mary, you can unmute yourself.
Okay, so basically I'm planning my future right now as well. And I am not sure, except for I know that I want to go into biology, like what you did. Do you think that to get to where you are now, that there's like a more direct pathway to it? Or do you really think that taking and studying biology, systems biology, just continuing to progress and build up like all your knowledge, all the assets, all the skills. Like, do you think that that made you be able to do the job that you're doing right now to the capability that you are doing it right now?
Interesting question. So there are two ways I could answer this. The first is that I don't think I would have ended up here without the steps. And so that's not the same as because I did these things, I ended up here. The fact of the matter is sometimes things just aren't linear. And so while you can absolutely plan for things, my strategy has always been build the skills that I think I'll need at the next level, and then let the next level kind of find me. With that being said, I also do not think I would have been here without these skills. And so in general, there are skills that are just generally transferable, and I like doing a lot of things. And so I think that's what's helped me get here. There are also people that don't, right? They know they want to be a researcher. They want to do research every day. And that's the career that they want to follow. And so instead, I think it's how do you make career decisions that validate and enforce you're making decisions that you actually want to do. And learning what you like and what you don't like are equally important. And so at some point, I realized that I did not want to stay in research. And so that's when you have a pivot, but I don't think I would have known that had I not done it. And so there probably is a more direct route, although I started my PhD 10 years ago. Oh my gosh, that's crazy. I started my PhD 10 years ago, and quantum computers did not exist on the cloud then. And so there is no way that I could have like intentionally planned to be working in quantum computing as a product manager, because the product field in quantum computing didn't exist then. So like I could have been a physicist doing research, but the current role that I have did not exist. And so I think that's the other thing to think about, especially when you're working at the edge of some of these new technologies. Like the field has changed so much. So I'd say plan and be strategic, but don't over-engineer it, because life and things will happen and you want to be ready for it. And I wanted to get a PhD my whole entire life, and then I finished it and I was like, now what? So sometimes even when you do things according to plan, it still isn't exactly what you wanted. And so you can't over-engineer for things either. No, quantum computers do not have a RAM. There is something called quantum RAM that people are trying to build. That's one of the funky things about it. Quantum computers contain all of their quantum mechanicalness, if you will, when the qubit is coherent. And so that's at that point where you're manipulating it, then you measure it and it collapses. And so it's at that point where the state is observable. It's why people often tell a bunch of physics jokes about cats, like, oh, is it dead or not? Is it the Schrodinger's cat? Like, oh, you can't see it until you measure it. And so the concept of quantum RAM has been proposed. It actually existing does not exist yet. And what we've been telling people is to think about quantum processors as kind of like a companion to a GPU. And so if you know anything about the history of GPUs, obviously they didn't start as we know them today. And so instead, they're now these like things that go with computers that make them do really specific tasks better. And we think that quantum processors will also exist in that way. And so we have this initiative at IBM that's really focused on quantum-centric supercomputing, where we imagine this world where you have a classical computer, a quantum computer, a GPU, and you're outsourcing different hard tasks to the things that are best equipped to do it. And yes, we have partnerships with startups. Actually, a great friend of mine, his name is Stephen Ellerington. If you ever want to look him up on LinkedIn, there's another Black guy that got his PhD from Yale, manages our startup program. And then actually another friend who is a Black woman that got her PhD from Harvard. So I actually get to work with a lot of people that look like me that also have PhDs. She does a lot of work with our accelerators and our deep tech companies. I'd say that investors are still warming up to quantum computing, especially since we had a very interesting just general tech and investing boom in the past 2 years and like pre-pandemic. And so that's slowing down a little bit with the recession. Just investment in tech is changing. And because quantum computing is more of a long-term initiative, I think investors are still wrapping their head around it. I also know a few investors, and a lot of them always say they only invest in things they understand. And I think that some of them don't quite understand it yet. So we're still getting there when it comes to investors and accelerators and those sorts of things. But there are specific accelerators that focus on quantum computing. So there's one called Duality that's based in Chicago, the Creative Destructive Lab. There's one in something like that that's in Canada that's focused on it. And so we're starting to see more of them pop up, but they kind of have the same portfolio of startups in quantum that they're working with. Cool. Well, thank you all for the time. I enjoyed it. I did drop my LinkedIn, and so if anyone wants to follow up or has more questions, absolutely let me know. I generally post about things like jobs and like other things on my LinkedIn. And so if you happen to apply, also drop me a name or drop me a note.
Yes, thank you so much, Kayla, and thank you for giving your time. Just one request, if possible, would you be okay with sharing your presentation from today? I could email it out to you.
Yeah.
Cool. Yeah. So yeah, once again, thank you, Kayla, for your time. Thank you to Verizon who helped sponsor this program and initiative. And as Kayla said, you guys will find her on LinkedIn. When we do our follow-up email, guys, I'll include your LinkedIn, a recording of tonight, and the presentation. So thank you all. Guys, Camilla just dropped in a form. We want to keep doing events like this, so we need you guys to fill out this feedback form. If you don't mind, please click the link and give a survey so that Verizon can continue to support initiatives like this to help you guys, build more diverse pipelines into technology.
Cool. Thank you again for the invitation.
Yes, hope to have you again. Thank you, Kayla.
All right, bye.
Yeah, bye. Once again, guys, if you don't mind, just click that form and fill out that form. That helps us to keep stuff like this happening for you guys. Yes, thank you all for participating. You guys asked some great questions, and I think Kayla liked the group, so hopefully we can get her back and get internships for you guys. Fingers crossed.
For sure. It was amazing. Thank you so much.
Yes, thank you. Thank you, Mary, for being so engaged.
I am a part of a quantum group, so I'm going to tell them about this event and what you guys are also doing. And I'm going to tell all my engineering friends. And it was really cool because it's not a lot of times that you hear about, quantum and people who are working in the field. And just being here today, Kayla mentioned like 3 Black people. That's amazing. So I'm going to follow up with all of that. Thank you so much, Jeff.
Yes,
And yeah, what you guys are doing is amazing. Thank you.
thank you so much. I really appreciate that. And I want to say, maybe we should connect. You can shoot me an email or look me up on LinkedIn. And would love to learn more about what you're working on and seeing if the incubator can be a resource.
For sure. Thank you.
Yes, thank you. Okay, all. I'm going to close up the room. I hope you click the form link and have a good night. Thank you.